Sir, you can start. We are live.
Thank you. Good afternoon to all of you. Welcome to the MoES webinar series organized by the Ministry of Earth Sciences. Myself is Thamban Meloth from the National Center for Polar and Ocean Research. This is the 7th lecture, live lecture in the series of MoES webinar. During the last 6 lectures, you listened to the experts from ocean sciences, technology, and atmospheric sciences. And today, we would discuss on another sphere of Earth system science called the cryosphere. As most of you would know, cryosphere is that part of the Earth's surface where water is in frozen form. More interestingly, more close to our home, we would discuss today on Himalayan glaciers. In the coming 50 minutes, I will try to give you a glimpse of Himalayan glaciers and their importance as well as how they behave. So, Himalayan glaciers in a changing climate, that's our topic today. And my talk is structured in this way. I will discuss about cryosphere in general. What is it? What are its implications on global, regional, and local impacts? We would discuss the importance of Himalayan glaciers for the globe as well as other regions. We would also discuss the glaciers and the types and characteristics. I will also discuss how do we measure the glacier changes, what are the kind of techniques we use, what are the tools we use. Then I will briefly touch upon the status of Himalayan glacier systems. And very briefly, I will just give a glimpse of what MoES is conducting research on Himalayan glaciers. And finally, last but not the least, I will try to give a glimpse of the field challenges faced by the glaciologists in Himalaya. The World Climate Research Program, which is a leading body of climate researchers internationally, have found that melting ice and global consequences is one of the 7 grand challenges. Among the very highly difficult questions, this is one of the very serious questions to be answered. However, major challenges in the quest for better predictability of cryospheric changes remain in the 3 main interlinked areas. One is observations, means it's extremely difficult to get very good observations in remote regions like cryosphere, and you need more observations. Process understanding, which means to understand the governing mechanisms, how do glaciers behave, very critically need to be understood, and the modeling capabilities. Compared to atmospheric as well as ocean sciences, the modeling is still at infancy in cryospheric science. Therefore, we need to know more. As you know that cryosphere has large areas including not only just glaciers, but snow cover, ice caps, ice sheets, sea ice, and frozen ground. Globally, Antarctic ice sheets constitute 91% of the frozen water. As many of you would know, Antarctica being one of the very large continent, which is the size of nearly 4.3 times of Indian subcontinent, which is covered nearly by 98% of its surface by ice, where ice can be as thick as 4 kilometers. Therefore, it has the 91% of the total frozen ice. Followed by Greenland, which constitutes nearly about 8%. Greenland is in the Arctic. And the mountain glaciers, which are mostly found in the tropics and other areas, temperate regions, constitute only 1% of these glaciers. But they are distributed across the continents like Himalayas, Alps, Andes, and so on. And they are also situated at places where most of the world lives, where the population is the highest. Therefore, their impact is can be nearly 35% in terms of how they impact the people. Therefore, remoteness and challenges faced in cryospheric regions are the important ones to be first answered before you can carry out research in cryospheric regions. Among the cryospheric regions, we often hear about polar regions, the Antarctica in the southern hemisphere and Arctic in the northern hemisphere. Antarctica being a continent completely covered by ice. Arctic, other than Greenland, you also have sea ice cover. However, there is another part of the polar regions recently named as third pole, which constitute of Himalayas as well as the Tibetan regions, which contains world's largest mountains, including all 12 peaks above 8,000 meters, which is also source of more than 10 major rivers and also from the major ecological buffer zone. It not only consists of glaciers, it also constitutes the permanently frozen land. If you look at the impact and importance of glaciers, it can be categorized in three forms: global, regional, and local. Globally, the glaciers and cryosphere are extremely important to understand this global sea level rise. In fact, it is one of the least understood among the sea level rise variables. It is also very important for the globe's energy balance, because ice being a highly reflective surface, it can control the global climate system. It also influences the ocean circulation across the globe. If you look at regional terms, the countries which are nearby these glaciers significantly depend on water, energy, agriculture, and its entire economy. If you look at local terms, glaciers are places where most of the nearby towns live because of the local tourism. When local agriculture specialized to these mountain regions, and sometimes there are hazards like avalanches, landslides, sometimes glacial lake outburst. These are the things impact of some of the glaciers across this region. If you look at the last nearly 200 years of climate record, especially the temperature record, globally average temperature record, you find that, in fact, this particular record shows basically global temperature anomaly. You find that since 1980s, there has been a significant increase in temperature happening across the globe. This is consistent not only on the land, but also in the ocean. However, compared to temperature record, our understanding of this cryosphere or the glaciers are very limited to last, say, about 50 years, or even better records are available only for the last 40 years. However, these 40 years of glacier records given in this particular graphs, tell you on the right hand side, it shows the cumulative loss of ice on these glaciers. Systematically since 1980s till 2017, we find a loss of nearly about 20 meters of water equivalent of ice being lost. It's not only that, the yearly ice loss, which can be seen in this bar graphs, have been also systematically increasing since last few decades. So the loss of ice seems to have a direct relation to the climate change. If you want to understand Himalayan system, we first want to understand the Himalayan arc, which is the huge mountain chain sitting over there with countries like India, China, Nepal, Pakistan is bounding it. There are two things you have to say. One is the climate system is essentially controlled by the monsoons. In fact, Himalaya has its own influence on monsoon system, as well as Himalaya is also influenced by the monsoon system. Most of the moisture comes to the Himalayas because of monsoons. However, in the western Himalaya, we also have a moisture source coming, especially during winter time, from the Mediterranean region, called through the western disturbance, what we call as a westerlies. The influence of monsoon decreases as we go from the east to the west, and dominance of westerlies takes place basically along the western Himalayan region. If you take a transect across Himalaya, because we all know that Himalaya is formed because of thrusting of Indian subcontinent to the Eurasian landmass, we also find, therefore, the topography from the Indian side as we go from the plains to the high mountains, very steep increase in this topography compared to what you find in the Tibetan region. This has also implications for understanding the cryosphere. So therefore, to study the cryosphere of the Himalayan region from the Indian side is much more difficult to approach, physically more challenging compared to than what you can approach from the Chinese side or the Tibetan side. So the third pole, which is essentially the Hindu Kush Himalayan region as well as the surrounding Tibetan region, with the glaciers as well as the land which is basically permanently frozen, is home for nearly more than 12 major highest peaks, more than about 8,000 meters, including Mount Everest and K2 and Kanchenjunga. It's also home to large number of glaciers regions and home for 10 major river systems, including Indus, Ganges, and Brahmaputra. Therefore, the third pole has a huge significance on the economy as well as people life. Nearly 250 million people depend directly on the third pole for their lives and livelihoods. Nearly 1.9 billion people depend on Himalaya for water, food, and energy resources. And more than 35% of world's population benefits indirectly from its resources and ecosystem services. No wonder it has major global biodiversity hotspots. It is the largest reserve of ice outside the polar regions. It is a source of 10 major Asian river systems. And even more importantly, many of the culture and this system originated from Himalayan region, and it has got a huge biodiverse system, including several bird and biodiversity areas. So it is critical for life, economy, and energy needs of the Asian countries. If you look at, for example, Ganges, nearly 580 million people live in Ganges river system as well as its plains. Together with the Ganges, Indus, and Brahmaputra, nearly 900 million people directly depend on its water and resources. And if you look at the energy hydropower potential of these rivers, for example, Indus, Ganges, Brahmaputra itself, for India, it can constitute nearly about 150,000 megawatt power, of which India is harvesting only about 30% currently, whereas China is able to nearly harvest more than 86% already. So there is a huge potential for the energy demands of the country as well as the nearby developing countries. So there is no wonder why people call the Hindu Kush Himalaya or the third pole as a water tower of Asia, because all major 10 rivers originate from this region, including Indus, Ganges, Brahmaputra, which control the food belt of India and also has the largest glaciarized basins in this particular region. This one particular graph tells you what is the total available glaciers in terms of area. There's nearly about 60,000 square kilometer of glaciarized basins in this, together with the Indus, Ganges, and Brahmaputra, out of which Indus constitute very large share of it. In fact, Ganges has very less glaciers. This means that the glaciers have a much more significance for the Indus Basin. It's not only that it decides the seasonality of water available, but also it decides the quantity of water available. In case of Ganges and Brahmaputra, it more decides the seasonality, not necessarily so much of quantity. Even then, it's very important. If you look at the inventory of Indian Himalayan glaciers, this is the one which prepared by the Geological Survey of India nearly 10 years back. It shows about nearly more than 9,000 glaciers across Indian Himalaya. This numbers varies depending on the method used. Sometimes the satellite methods tell you the larger numbers. However, the takeaway point from this particular graph is that the small glaciers, which is less than 5 square kilometers, constitutes nearly 90% of the number of glaciers in Indian Himalaya. I mean, even nearly 40% of the glaciated area. However, nearly 50% of the glacier ice volume is controlled by the large glaciers. Large glaciers bigger than 25 square kilometers. So the glaciers are different types, so they have different importance in different regions. Even small glaciers can be highly important in places where the people are living on its water. So what is a glacier? The glacier is essentially nothing but, in simple terms, it's a slowly moving river of ice. More scientifically, it's a thick mass of moving ice created by accumulation of snow which moves over a ground. In case of mountain glaciers, they essentially move under the influence of gravity. In case of continental glaciers like Antarctica, they move by its own weight. I've given you 3 pictures here to give an impression of how Himalayan glaciers look like. It has an area where new precipitation or new snowfall takes place. It has an area where ice is being lost. This one is a satellite picture. Again, gives you an impression actually what it looked like. So in a schematic, the characteristic Himalayan glaciers look like this. We have an area where snow precipitation takes place because of the high elevation and temperature. And the snow provides accumulation, the ice accumulation. Sometimes even avalanches can provide some more accumulation. So this area where the snow or the ice is always accumulated is known as accumulation zone. And the area where ice is continuously being lost or where the loss is higher than the gain is known as the ablation zone. The ablation zones in Himalaya can be also covered with the debris in many cases. The line or the area which differentiates the accumulation and the ablation, where there is an equilibrium, there is neither a loss nor a gain, is known as equilibrium line or sometimes snow line, because above which you'll find snow. There could be a lot of crevasses in the ablation area, and during the ablation, a lot of melt takes place, and the water could directly goes to a stream and then reach a floodplain later, or the glacier can create some lakes called glacial lakes, proglacial lakes, which continues to expand as the glacier retreats. Glacier brings a lot of material as deposits along with it as it moves and get deposited along the side, what known as lateral moraines. Moraine is a deposit, sedimentary deposit by the glacier, and sometimes this deposit could be as the glacier retreats, we can see at the terminus of it, known as terminal moraine. And if you look at the wind system, the local wind system in a glacier, we have essentially the katabatic winds, which are the gravity winds or the downhill winds, very cold wind. You can also have valley wind, which is essentially coming from the valley to the glacier because of the adiabatic heating. So this is how a glacier exactly look like in most cases. And I will keep repeating some of the terms and terminologies. So I just would like you to keep remembering that. That's what you see in a schematic. How it look like in a panoramic picture. You know, in a glacier in Himalaya does not actually exactly look like what you would be expecting unless you are used to that place. In this case, for example, the white area is what we call actually accumulation area, where ice is getting accumulated, and this blue line is the one which we call a snow line or equilibrium line. And the material what you see here is actually a glacier, what we call as an ablating glacier. So it's an ablation zone, because a lot of the mountains surrounding it, the rocks and rock particles get deposited over it, what we call as debris, and this entire glacier can be covered by debris and known as debris covered glaciers. And sometimes the snout or the terminus of a glacier could be just being lost in this debris cover. So understanding this particular picture would be extremely important when you go to Himalaya. And there are mainly two types of glaciers in Himalaya. One is a clean glacier, where the surface of the glacier looks clean relatively, and where you can see the fresh ice. And sometimes you will not find anything other than just cover of debris or the deposit of these particles. It's called debris covered glaciers. You find them most often in Himalaya. And it also has an implication for a health of a glacier. Typically, a glacier which is healthy will have an area which is much more cleaner, and a glacier which is relatively unhealthy or deteriorating will have more and more debris cover. How do we study glacier responses to climate change? Because we all want to understand how actually a glacier responds. Glaciologists use a term called mass balance for it. Mass balance of a glacier indicates the healthiness of the glacier. It is nothing but the net change of its glacier mass over a balance year. When we say balance year, it is not necessarily a calendar year. It is typically a year from when the snow or the ice start accumulating, somewhere early winter or the late fall, sometimes in October time. Then when finally the glacier completely gets melted away, somewhere in September. So that's what we call as a balance year. So in simple terms, it is a gain or loss of ice in a glacier system. And this cartoon again gives you an impression, a cross-section of a glacier, where you can see an accumulation zone as well as an ablation zone. An accumulation zone is where snow and ice get accumulated, essentially because of snowfall, sometimes because of avalanches from valley sides, and then you have formation of snow and firn. So in accumulation area, the input is always higher than the output. In ablation zone, where the loss of ice happens or the melting takes place, is known as the ablation zone, where the output, mainly because of the evaporation, sometimes because of sublimation directly from glacier to evaporator, get it gases, it becomes sublimation, sometimes by melting. So in a ablation zone, the output or the loss is always higher than the input. So there is this zone of equilibrium, where there's a balance from gains from accumulation as well as the losses from the ablation. It's also known as snow line. Because since temperature as well as the climate variability can influence the availability of snowfall or the precipitation, as well as the increase in temperature can lead to loss of ice, therefore glacier mass balance or the health of a glacier is a sensitive indicator of a climate change. So how do we measure glacier mass balance? There are mainly four methods I will discuss here, the predominant ones. One is a glaciological mass balance method, which is a direct field method, very accurate, but it's also very laborious. Then the energy balance method, which enable us to study the present and future changes. Then there are indirect methods like geodetic mass balance method, which is ideal for long-term time scales. And of course, there is remote sensing based method, which are again indirect, but it has a potential for large areas. However, as in every remote sensing method, you still need to have a validation and calibration. While there are different methods, these different methods are basically essentially complementary to each other. There is no existence for only one kind of method. In coming slides, we will discuss a little more detail of each of this method to give you an impression how actually people carry out the study of health of glacier. The traditional glaciological mass balance method, which is the most direct and most accurate method. Again, you see a cross section of a glacier here. You find an accumulation zone where ice is getting accumulated, and in ablation zone where ice is being lost. And then there is an equilibrium line. What we want to understand when you study a glacier is that how much ice is getting accumulated in a year, a balance year, and how much ice being lost. So people need to visit the glaciers sometimes early summertime before actually the melting takes place, and start measure the first how much accumulation of snow happened during the winter period or whichever the accumulation period, as well as later on during summertime how much getting accumulated. How do we do that? People go to field and make a pit with on hand and then dig out a part of the ice and find out how much ice was actually deposited during last that particular season. That will provide you, as well as this, people also study its characteristics like density and other parameters, which will provide them an estimate how much ice got accumulated. And to study ablation, we need to measure how much this is being lost. How do we do that? We install these small stakes or sticks properly measured priorly and drill deep into this glacier, nearly 10 meters, because sometimes the melting can be very high, so you need to drill very deep and install them and measure them, and then visit again later during the later part of the summer or the ablation season, when some of the ice is lost and the stick must have been fallen down. Then you take a measurement of what is there and exposed on top. That will provide you the amount of ice being lost. So this will give you a very simple, straightforward, direct method. However, it's not as simple when you have to carry out this work during very difficult and challenging conditions. So these are pictures how accumulation zone measurements are made, like digging a pit and taking measurements of density and so on. Sometimes, if you are lucky, as well as if you are good enough to carry out glaciological work, you can also get this kind of exposed areas where you can actually create a snow stratigraphy year after year, how much snow is being accumulated. That provides you a lot of information for modeling. For ablation, the techniques, as we discussed, we drill using a drilling system and then establish these long stakes deep into the ice. And as the temperature get warmer and this get exposed, you make measurements of that place, how much this one, as well as you take a GPS measurement. Then you can make a map of these sticks or the stakes installed on top of the glacier where ablations on the red spot and the accumulations on where the blue spot where you have made a pit and measured the accumulation. So this is how it looked like. Another method, what we call as energy balance method, essentially employs on the fact that energy exchanges between atmosphere and glacier surface control the net energy available for snow and ice to melt. That means you need to make measurements of surface energy fluxes over a glacier. You would also need to employ some models. So you need to establish a very full-fledged automatic weather station on top of the glacier, which measure all the meteorological parameters as well as radiation fluxes and other related parameters, not only over a glacier, but also in other part of the basin to get a larger picture and to do a better modeling. So by calculating surface energy balance, glaciologists can actually estimate the change in glacier melt rates and mass balance. The surface energy balance is nothing but the sum of all energy fluxes at the glacier surface. The energy required to melt the ice is nothing but the sum of net short wave radiation, net long wave radiation, and net turbulent heat fluxes like sensible heat as well as latent heat wave, as well as the ground flux. Through careful evaluation of energy fluxes and employing models, we can estimate the mass balance changes. This model can be sometimes point-based, because if you have a AWS system in one place where you have the very good control, you can make a model for that particular point, which is known as a point model. If you have a sufficiently good information about the entire glacier itself, and you can also create a very good digital elevation model of that glacier, then you can distribute it, the energy fluxes, and make a distributed model. If you have sufficient information across the glaciarized basin, which includes several glaciers, you can what you can call a distributed model for the entire basin. So you can understand it's a very useful method to understand the current, not only the current changes, but also you can model for the future. So it's an extremely useful method. However, when you discuss about the Himalaya, you should also understand creating such a network of AWS system across the mountains and on top of the glacier, making them work through 24/7 is not a joke. Most of the time, many of the AWS system will have some problem. So therefore, one need to be a little bit skeptical about the amount of data you can get from all glaciers. The third method, which is an indirect approach called geodetic mass balance, is essentially done through an analysis of the elevation changes of a glacier surface at different times, sufficiently separated. Sometimes it could be decades long, to estimate the change in volume of a glacier. So the geodetic method can be applied using topographic maps, digital elevation models obtained by either aircraft or satellite imagery, and more commonly these days by airborne laser scanning. So in a airborne laser scanning, you scan the entire glacier, create a digital elevation model using the available data, say about 10 or 20 years back. You get again a very good image of scanning of this glacier again after some period. Create another digital elevation model. If you can create or have an assumption of certain changes in density parameters, what you can create is a change in mass. Essentially will provide a mass balance. It's actually very accurate for long-term changes. So therefore, the geodetic mass balance method is very commonly used for the decadal or longer time scales. However, it is not without any difficulties. There could be errors in the original digital elevation models, which can propagate through time. There could be errors, especially in Himalaya, where sometimes the glaciers are very steep. There, these errors can be very high. And we also make a lot of assumptions related to ice properties. Finally, we will discuss about remote sensing method. As in every field like oceans, atmosphere, and other research fields, the remote sensing has changed the way how we can study glaciers. Mainly because in situ field measurements of glacier mass balance are laborious, limited in extent, time consuming, and expensive. And using satellite-based different sensors like optical, microwave, as well as altimetry sensors, you can make a wide range of glacier measurements. And very commonly, you can create a very good inventory of glaciers by mapping glacier extents. You can also determine the elevation changes and volume changes. You can measure the surface flow velocity, and you can measure the snow line changes, which is what we call as equilibrium line changes. They are very typically can be studied on glaciers. However, as always, remote sensing method require calibration as well as validation. So you need to have, again, field studies. And also it is not ideal for small glaciers also with very high debris. Again, depending on the kind of sensors you use it. One commonly used method is known as the accumulation area ratio method, which is very widely used in Himalayan glaciers. It is nothing but the accumulation area ratio is nothing but the ratio of the accumulation area to the total area of the glacier, which will provide you an understanding about the mass balance of a glacier. For example, in this case, a glacier which our team is studying, if you can create a very good map of the glacier and its boundaries, especially during the late ablation period, sometime in September, when you know very clearly the ablation is nearly complete, you can differentiate the snow lines. So you know that what is an accumulating area where there is no melting will take place anymore, and where there was an ablation happening or the melting was taking place. With the ratio of this one, you will be able to finally get a mass balance of the glacier. So this can be done very good if you got a very good satellite data, like in this case, very high resolution satellite data, as well as you need to have some kind of field measurements. So far what we learned is understanding the glacier mass changes. In a changing climatic scenario, it's not only important to know about how much glacier mass is being lost or gained, it's also important to know how much it is contributing to a hydrological system. like a river system. How much ice is actually contributing to streams and rivers? So you one need to take measurements across the basin, river basin, starting from where the water is originating from the linear glacier till end of that stream where it joins a larger river. So you need to make a series of measurements in very challenging conditions to get an estimate of the actual glacier contribution to rivers. So these are some of the techniques we use it. The classic method of creating a hydrological station with a, once you know the cross section as well as you can measure the amount of water flowing through it at a different time throughout the ablation period, you can actually estimate how much water is being flowing through that. However, this is very complicated in many of the glaciers or many of the terrains. So nowadays we use methods like automated methods which can measure continuously using radar technology the height of the changes in the water which is flowing. That will provide you information throughout the year without being present. Sometimes you will have to have also manually still take a measurements to know how much water is there actually flowing and what is the depth of those rivers. So we learn now the methods to understand the glaciers, the changes, especially the glacier mass as well as the water. Now, what is actual status of the glacier changes happening in Himalaya? One of the simplest and very attractive ways to, if you are fortunate enough to have a photograph from large glacier-based areas, and if you take a picture about after several decades, you will have a very visually appealing as well as a dramatic picture which will tell you what's happening to glacier. For example, in this case, a picture of 1921 taken by none other than George Mallory, who was one of the famous British explorer, was part of the earliest Everest explorer, who took this picture when he found that it's a big glacier happening there. In fact, this is also part of that main Rongbuk Glacier. The eastern Rongbuk Glacier is currently considered as the highway to reach the Everest summit. The picture, which is taken later in 2009 by David Glaciers, again an explorer as well as a movie maker, very famous movie maker for that matter, he found a picture exactly at the same vantage point. What he found is a very dramatic change in this much time period, nearly 90 years. The glacier, which was flowing very beautifully, is completely lost now, where the area is filled with water now, and it provides you a very dramatic way of understanding how the status of glacier is changing. It is very good for telling the policymakers. However, this does not give you actual quantity of glacier being lost. So traditionally, people were trying to understand the changes of a glacier terminus change, which is the easiest place to approach a glacier. For example, in this case, the Gangotri Glacier in the upper Ganges Basin, this small part is where you can actually approach the glacier. And you can make a continuous measurement. If you have it, it will tell you as the glacier is retreating through time. It will provide you again a very good information about how the glacier is behaving. So these information, the terminal retreat, are very useful and found to be in Himalaya, showing that nearly 20 to 30% of glacier being lost using this method. The number changes from as less as 3 meters per year to about even 40 meters per year. It's a large enough, big number of change, and it can change based on various factors. However, this still does not provide you very quantitative information. You still need to know how much area is vacated and how much the volume of ice is being lost, which is more important in quantitative terms. So people use a geodetic method. In this case, actually, for the last 40 years, available data across the Indian Himalaya, which shows a continuous decrease of mass of ice. Nearly about 20 meter water equivalent is being lost during the last 40 years, which is nearly that of the global average. And however, you should also note that these are various glaciers people have been studying it. Some of the glaciers only recently started studying it. So the data available, many glaciers are very limited. The bottom picture or the graph the bar graph tell you the number of studies carried out across Himalaya, which varies from less than 1 or 2 glaciers to about up to 15 glaciers studied in a given year. There are times when you have very little information across Himalaya. Even then, on an average, we have less than 10 glaciers studied across Himalaya, which means that among the nearly 10,000 glaciers in Himalaya, we are only studying still less than 0.1%. It's a very less number, but this is the only possible number. Still, at least we have it. Therefore, more and more data is still required from these glaciers to have a better control about our modeling of this glacier change. So this gives another dramatic panoramic picture of a glacier. What happens to a glacier with a continuous loss of ice mass? In this case, this is a Liroom Glacier from Langtang Valley in Nepal, in central Himalaya. What we find that the glacier was somewhere here, and the terminus of the glacier is somewhere sitting over here now. It's been continuously losing mass, and even a small lake is formed down here. And even the glacier area, or the ablation area, what is name written here as AB, it's been continuously losing mass, and many places it does not have any ice left, only debris is there. And accumulation is very small. So there is no real feeding of glacier happening to this. This gives you a picture of a classic case of a dying glacier. In fact, people living down valley of these glaciers are really feeling the heat of it. Tourism is affected, the water availability is affected. So this is what actually really happens to a local community when a glacier gets lost or slowly die. So the retreating glaciers are not only just retreating, but they are also creating, as in many earlier cases you have seen, creating a lot of these lakes. And as the glacier is retreating, the lakes are expanding. The glaciers, as they vacate from this region, the lakes which are formed on small ponds becomes large lakes, but still they are protected only by moraine or the material which is brought by the glacier. They are not very well dammed. So sometimes, as a glacier is continuously retreating and the moraine lake or moraine dam lake, moraine is nothing but a deposit of a glacier, which will be very unconsolidated, therefore it's not very well cemented. So as the water continuously increases, by any means, sometimes by mechanical breaking of a glacier, sometimes by a very extreme weather like cloudburst or something, you can suddenly this can overtop, which can be what we call actually a dangerous case for called GLOF, or the glacial outburst flood, which happens in many cases. In fact, many of you must be remembering the Kedarnath tragedy of 2013, when, because of very freak weather, the extreme precipitation due to a cloudburst, more than nearly 400 times of a typical monsoon rainfall occurred within less than 1 day, melting away the glacier, the Chorabari Glacier in the upper Ganges Basin. And there was a lake here called the Chorabari Lake. It could not withstand any more water and the slush and the large boulders falling over it. It gave away, leading to a flash flood, killing nearly 6,000 people in the Kedarnath town and down villages, and completely changing the way currently the villages look like. So this tells you what can go wrong if you don't even monitor these small lakes. Across Himalaya, we find several such small lakes being formed, and these lakes are being continuously expanding. Kedarnath was only a case. Kedarnath was a classic. It is not a case of a clear GLOF or the glacial lake outburst, because it's a freak weather. However, the situation is same. Anything can happen to such glacier lakes can lead to a geohazard event. Therefore, it is also equally important to study these lakes being vacated by the melting glaciers. This is one of the picture from our own study area in Western Himalaya, the Gepangat Glacier, where you can see the accumulation as well as the ablation area, and the ice being mechanically carved, being lost here to the lake. And this lake has been expanding since last several decades. One of our studies shows that the glacier was earlier somewhere here in 1971. The glacier is retreated so much And as the glacier is retreating, the lake, which was very small, expanded not only in terms of area, but also in terms of volume. So the volume of this particular lake, Gepangat Lake, is expanded nearly 20 times. And believe me, this material which is stopping this lake is only just the terminal moraine material, the marine material, which is very unconsolidated. It can go anyway, loose. And there are villages below this particular such glaciers, and they need to be much more, need to be monitored and warned. In 2 slides, I will just give you a glimpse of what MoES is conducting research in Himalayan cryosphere. The Ministry of Earth Sciences as well as NCPOR started the glacier research in Himalaya only 6 years back. With a what I call limited time as well as limited resources, what we have been trying to do a comprehensive, at the same time very integrated study of across Himalaya, not only by NCPOR itself, by through a project called HICOM, where we coordinate multi-institutions to study the glaciers as well as the impact of climate on these glaciers and its hydrology. Several institutions are partners to it. NCPOR itself is carrying out in one particular basin called Chandra Basin. So therefore, we are able to get data across the Himalaya with very limited resources. NCPOR conducted work on a Chandra Basin, which is in the Himachal Pradesh, in Lahore Spiti region, which is again a very large basin, which covered with a very high glacier content. The basin area itself is about 2,400 square kilometer area, of which glaciated area is about 700 square kilometer. And we are studying 6 benchmark glaciers out of in this basin, like as big as the Barashagiri, which is the 2nd largest glacier in the Indian Himalaya, and also the small glaciers like completely debris covered glacier like Batal, and also glaciers which is terminating onto a lake like Samudratapu as well as Gepangat. We have set up a series of measurements across the glaciers, set up several AWS stations in the basin. We also installed several water level recorders, the yellow point water level recorders along the stream as well as the river, till the river joins to another river. So our study during the last 6 years tells that mean mass balance of these glaciers in Chandra Basin is negative, about on an average about -1 meter water equivalent per year. And it varies from glacier to glacier. In some of the glaciers, 1.5 meter water equivalent, or in some cases, it's only about 0.5 meter water equivalent. It depends on the size of the glacier, depending on the factors like debris cover and the other things like lakes, etc. So these glaciers are continuously losing masses for sure. And we need to study it. So we also have set up a station in this particular region called Himans, which provides you the logistic support system for approaching all these glaciers in this particular basin. It has its own laboratory as well as place for people to live. In coming few slides, I just want to give an impression about the challenges involved in Himalayan research, especially the glacier research. As I told you in the very beginning, Himalaya is situated in such a very high altitude, and even some of the glaciers are perched at places who are highly inaccessible, requires a lot of tremendous amount of field work. This is also one reason why you keep hearing a lot of people complain about that there are no real glacier data available in Himalaya. Simple reason is that it's approaching the glaciers and getting data is not a small task. Many cases, you may need to walk several days to reach a glacier, and even climbing steep slopes with the entire weight for your camping as well as for your living. In this case, like for example, 70-degree slope, you can imagine the kind of hard work involved in that. Sometimes you may have to even cross, a small river formed by these melting glaciers, which looks very simple. There is a cold water. You need to walk with barefoot on this particular small streams, and the flow can be highly unpredictable. You never know. Sometimes people fall into it. So to reaching a glacier does not look so simple as what we think. And sometimes, reaching one glacier to another glacier, you may need to climb or use the rope techniques that means one need to be a very good mountaineer to reach study glaciers, because during summertime the flow on the rivers can be very high, and you may need to be a little more adventurous if you want to get very good quality data. And in cases like some of the glaciers like Badashigiri, which we are studying, will require nearly 30 kilometers to be trekked to reach a glacier. Means you need 3 days to reach a glacier, camping on the way. So the only way to manage yourself is you are in isolation, without any communication as well as without any others. You need to carry your own things, in this case like the stakes to be installed on the glacier. It looks very romantic when you see it, because you're all alone and you can cook your own food and eat. In this case, my colleague is making his tea on its way, but it can be very, trying for many people. Like reaching sometimes some of the accumulations on the glacier, you may have to cross the crevasses. And reaching crevasses, you need to be a very good, again, mountaineer. You need to be properly prepared for it, with again still carrying all your weight while traveling. So it can be a very difficult, and in this case actually is taking accumulation measurements after reaching that accumulation zone. In some cases, you may have to climb down using ropes to make good measurements of a accumulation happening throughout the years. Again, my colleague is hanging and then is taking measurements of sampling as well as density measurements. And glacier weather can be highly unpredictable. Many times when we prepare to go to reach a glacier, you typically prepare for about a week. By the time you reach a glacier, the weather could completely turn havoc. You may have to wait in camp for days together, being unable to make any measurements. Sometimes when you start making measurements or setting up an equipment, suddenly weather goes havoc. So the glacier weather can be the one which is actually a big culprit in making very good data coming out of the glaciers. So in a nutshell, what we discussed today is, in this talk, is that Himalayan cryosphere is critically important for climate, life, economy, and energy requirements of the Asian continent. And defrosting of Himalaya in a warming climate has significant influence and implications for sustenance as well as safety of the Himalayan states. And we also found that Himalayan glaciers have unique features and characteristics which makes them an exciting and as well as challenging area for study. We learned the methods to study the mass balance or the health of the Himalayan glaciers could be very diverse, but which are complementary to each other. In situ measurements are very challenging, but there is no other way. You still need very critical for any accurate measurements as well as validation of any of the satellite data. Finally, for some of the youngsters who are watching my lecture, I want to tell you that quantifying the status and future of Himalayan cryosphere is an exciting area for research. Those who are passionate enough to carry out field work in challenging conditions, this is a place you want to do research. Thanks a lot for listening to my lecture, and I'm ready to answer any questions if any.
Dr. Thamban, that was a very interesting talk.
Thank you.
Thank you. And here are the questions for you. So I will post it in your chat window so you can see that and answer.
Okay, I'm ready for it. Have it posted already? Okay. Yes, let me read it once before I can just give some answer. Okay, the first question is that there was a news about green algae in Antarctica. Does the phenomenon occurs in Himalayas too? What are the repercussions, if at all, when it occurs? Such algae and deposits are very common across all glaciers. You find every glacier, in fact, the albedo of a glacier is basically decided by such a algae, organic materials, and so on. So you can find it may be green algae or it could be any other algae, and it could also be other organisms which sitting on the glacier always have some implication because they reduce the albedo. So they relatively they try to make the melting faster. That is the basic implication. Question 2. Can you explain radiation of which frequency can be absorbed and reflected, penetrated in the mass of the ice, and can we relate to this with the past insolation and glacier mass? See, what I will not go very detailed on this to this one, but what I can answer is essentially we are just measuring the shortwave radiations, the long wave radiations, the net incoming as well as outgoing, and then making a flux measurements. So I don't have other details at the moment. Is the melting of Himalayan glaciers less compared to Greenland? If yes, why? How is the health of Indian side of Himalayan glaciers at present, good or bad? This comparison is not a straightforward. Greenland, being a very large glacier or large ice sheet, it is not a glacier. It's got many glaciers, coming to the ocean. And for the past few decades, its rate has been expanding very, very substantially high. And Greenland glacier does not have any debris cover. So these comparisons are not straightforward, but if you see the latest reports of Greenland happening, the loss has been very substantially higher, possibly even higher than some of the Himalayan glaciers. But as you must have seen some of the numbers which I was talking about, the variations in the Himalayan glacier itself can be very small as to very large. So it's a question of what you compare it with what. Would continuous seismic infrasonic measurements using network could be considered along the terrestrial laser scanners to be considered as a nodal program? Of course, even I did not mention many other methods, the other methods of measuring glacier mass, like in a MoES program itself have different methods, like we are using terrestrial laser scanners for that matter. You can also think about making other measurements LIDAR based and so on. But in all cases, the biggest problem is you still need to reach to those glaciers. And operating instruments as well as even small drones over the glaciers are found to be very challenging than what we imagined. So it is not very easy to just give one answer to it. Of course, it could be very useful, but how logistically it's going to be working out for all glaciers. Finally, from the monitoring of glaciers for the last decade or so, how is the health of Himalayan glaciers? If not good, what measures are need to be implemented by government to protect glaciers in Himalaya? As you must have seen some numbers which I was showing, the glaciers have been retreating sometimes on an average per year about 1 meter ice is being lost. That means most of the Himalayan glaciers, not only what we study, 99% of the glaciers in Himalaya are losing mass. And as increasing, like if you must have seen the temperatures also rising, we also find that there is a clear relationship to it. But it varies from glacier to glacier because there are other factors other than purely on climate. And the health is certainly not good, but there cannot be much can be done by the governments on it, because these are natural happening things like rising temperatures. It's a global phenomenon. And things what happens in Himalaya, for example, the fall of debris on ice and actually helping to melt away, it's actually again a very peculiar case of Himalaya itself. It's not something which governments can directly do other than stopping the increase of what you call the black carbons and other thing. But you still have a large amount of dust which is naturally happening in Himalaya. So the black carbon or the what you call anthropogenic created dust or the aerosols are only a small part of that the picture what you're talking about. That's all which I want to say. Thank you very much. Once again, thanks to Vinu Valsala as well as Indian Institute of Tropical Meteorology and Ministry of Sciences for this opportunity, and for all of you for taking your time to listen to the lecture. Thank you very much. Have a good day.
Thank you, Dr. Thamban. Thank you very much for spending your time for this webinar. Thank you very much for answering the queries. So we can go offline now. Thank you. Thank you all.